Hello, welcome to section 2.2. Today we are going to be talking about introductions to polynomial functions, and most importantly, we are going to be discussing the end behavior of different types of polynomial functions. So let's start by analyzing polynomial functions with multiple terms. One important characteristic is the end behavior. So how does the polynomial behave at the endpoints? So usually when we have a graph of polynomial, it's either increasing or decreasing. Is it going to infinity or negative infinity? So we want to start by what's going on as x approaches infinity. So what happens to the function as x goes to infinity? X approaches infinity. That means that x becomes very, very large. As x goes to negative infinity, we have it's becoming a very, very small number, a very large number to the negative direction. Now, what does that behave when the function entirely, or the y value, so this is the y value, goes to infinity and the y value goes to negative infinity? So we begin by discussing how does a polynomial look like. For a polynomial f of x, these a sub n's are your coefficients. Those are your coefficients of your leading term. So x of n, this n is your leading term. We can observe that it will have a general direction. And who will determine the orientation of the graph? It's that first term, a sub n, x to the n. Now we have to look power, at the power of the polynomial and what happens when the coefficient is either positive or negative. And that's when we discuss endpoints. So when we have the function a sub n, x to an even, so 2n, an even function, an even polynomial, what happens as x goes to negative infinity? So a sub n is positive, our coefficient is positive, but what happens as x approaches negative infinity? Well, we have a negative infinity to a positive power. That means that the endpoint will still be positive. Same thing here. So my endpoints of those particular values, what happens as it's approaching negative infinity, my endpoint, so see how my x is going to negative infinity, but the y value is still positive. Now what happens as x goes to positive infinity? I'm going this direction. So for example, as x goes to infinity, my y value will also go to infinity. So here I'm looking for an x squared, an x to the 6th, an x to the 8th, and my coefficient a sub n is positive. So a sub n being positive will always have f of x always going to positive infinity. Now we will have a different case if a sub n is negative. Now how will that change? Well, now if a sub n, the leading coefficient, now let's look at this leading coefficient, a sub n. What happens when a sub n is negative? If the coefficient is negative, what happens at x sub n goes to negative infinity? So we have a negative a sub n, x to the 2n, or n as n being an even number. Now we will have this behavior. As x goes to negative infinity, my y will also be negative. So now this is negative x squared, a negative x to the 4th, a negative x to the 6th, and so on. My power is even, but my leading coefficient is negative. So here I have to focus on, okay, what's my leading term? My leading term is negative, so my y value will be negative. If my a sub n is positive, then for an even polynomial, then my y value will be positive. Okay. Now those things change if my polynomial is an odd polynomial. If I have an odd polynomial, then a sub n is positive. Then I have a scenario like x to the third. What happens as x goes to negative infinity? Well, then y will go to infinity. So this term, even though a sub n is positive, but a polynomial is odd, then you will have this behavior. As x approaches negative infinity, y will be negative infinity. Now, as x approaches positive infinity, so as x approaches positive infinity, so going this way, as x approaches infinity, then y will also go to infinity. So then notice here that my graph, as x is going down, then y is going down. As x is going up, then y is also going up. Now that's when your a sub n is positive. But what happens if a sub n is negative? If I have negative x cubed, now what happens? Your orientation changes. So as x goes to positive infinity, your f of x will go to negative infinity, and I have this behavior. As x approaches positive infinity, my y will go down, so it's reversed. Now, as x is going to negative infinity, which is this direction, as x goes to negative direction, then y is going up. So as x goes to negative infinity, your f of x will go to positive infinity. And that is called the end behavior. That's a negative x cubed, a negative x to the fifth. It could be a negative 7 x to the seventh. My a sub n is negative, then I will have this behavior as x approaches negative infinity, as x approaches positive infinity. So using that information, we are going to go to the following examples. Alrighty, so now let's go over some examples on how to determine the end behavior of a graph. So the first thing you have to notice, step one, is what is the leading coefficient? What is the leading coefficient? In this case, the leading coefficient is who has the highest degree and the coefficient. So in this case, the coefficient a sub n, x to the n, x to the n is x to the fifth power, and a sub n is 1. So 1 is greater than 0, that means it's positive, and n is odd. So then we will have the end behavior, if we look at our notes, and if we recall, if a sub n is positive and we have an odd value, then what happens as x approaches infinity? What will happen to our function? Well, then as x goes to positive infinity, my function f of x will also go to infinity. And how can we check that? Well, we can check by two ways. We can graph the polynomial, we can graph, or we can test the function. How will the function behave? Will it go to positive infinity or negative infinity? So notice how x to the fifth dominates. What happens as x becomes a large number? If I have a large number to the fifth power, it's going to be larger than the negative 5x cubed. So I know that when I test the function as x goes to infinity, the entire function will go to infinity. So let's go ahead and actually graph this polynomial. Let me use my Calculate 84. That way I can share my screen and you are able to see the graph of that function. So what I have y equals, I have x to the fifth power minus 5x cubed plus 4x. That's the function that I have, and then I'm going to select graph. Notice here that this is the function of that polynomial, the graph of that polynomial. What happens as x goes to that right side? Notice that the y will also go to that positive direction. So that proves exactly what I'm talking about. As x goes to infinity, then the entire function will go to infinity. And that's because we have an odd polynomial with an a sub n being positive. Now here, this one's different because you can't really distinguish what the degree is. I have a leading coefficient of a -2, and look at the degree. I have an x term, and then I have an x to the third. So technically, this is x cubed and then x to the first. So x times x cubed, it's an x to the fourth. So my leading term will be -2 x to the fourth. Now here, my a sub n is negative, but the power, but s of x of n is odd. Sorry, n is even because 4 is even. So we have an even polynomial, but my coefficient is negative. And I had to do a little bit of work because I have an x and an x to the third. So whenever you have a polynomial that's kind of divided, you have to pay attention to the degree of each of the divided terms. So I have an x and then an x to the third. So combined is an x to the fourth. And don't forget that there's a negative in the front. So it's a -2x to the fourth. That is the dominant term. That is the dominant term that I'm going to look at. So a sub n is negative and n is even. So what happens as x approaches infinity? And what happens as x goes to negative infinity? So first, as x approaches infinity, what will happen? -2x to the infinity to the fourth power, but I have a negative in here. This is going to go to negative infinity. So f of x, so this function, f of x, will go to negative infinity. Here, -2 to negative infinity to the fourth, negative infinity to the fourth power, it's still positive because it's an even polynomial. So this is still a negative infinity. So it doesn't matter the orientation here because I have an even polynomial, but my leading coefficient is negative. So then this will behave this way. So as x approaches negative infinity, my y value will go to negative infinity. As x approaches positive infinity, my y value will go to negative infinity regardless. So we saw that both when x is positive infinity and when it's negative. Let's go back to the first one. So we saw what happens when x is positive infinity. What happens when x is negative infinity? Well, if we test the function, if we have a negative x value raised to the fifth power, my solution will still be negative. So f of x will go to negative infinity. And that's because we have an odd polynomial. Same, we can also look at the graph and test the function. So remember, if we go back to our screen, what happens as x goes to negative infinity? So you're going now this direction. My y is negative. So you can look at it based on a graph substitution. And then if we remove this graph and let's put in the new graph, and the new function is this -2 parentheses x minus 5 close parentheses open parentheses x plus 1 close parentheses to the third power. And then we're going to graph that. See how now, if I'm going to zoom out a little bit, see how my graph is going down. As x goes to negative infinity, my y is still negative. As I go to the right direction, y is still negative. So see how they're both going pointing down? That's because my leading coefficient was negative. So having a negative leading coefficient matters when you have an even function. It matters when you have an odd function. Okay. So that is n behaviors. Now, determining the zeros of the functions defined for which f of x is equal to 0. When I'm looking at zeros, that means I'm looking for x-intercepts, how many times it crosses the x-axis. So determining the zeros of the functions defined by this third degree polynomial. So one way to find zeros is letting f of x equal 0 and finding x. So it's like you are finding your x-axis, your x-intercept. So 0 is equal to x cubed minus 5x squared minus 16x plus 80. Now, once we have this, we have 1 term, 2 terms, 3 terms, 4 terms. we can factor by grouping. So we use the grouping method to factor and factor. So what can we factor from the first term? We have an x squared to factor. That leaves us with an x minus 5. The second term has a negative 16 because 16 and 80 have 16 in common. And that gives you x minus 5. Now this is set equal to 0. Because I have these terms to be the same, I can pull it out as one factor to be x minus 5. The other factor is x squared minus 16. They're both equal to 0. Now I can split using the zero product property, ZPP, the zero product property. The ZPP is the zero product property. And what does that mean? That zero product property means if this product and this product equals 0, each individual product is set equal to 0 automatically. So x minus 5, set that equal to 0. X squared minus 16 is equal to 0. Now here, this is easy to solve because that gives me x equal 5, moving the 5 over both directions. Now here, this you can use the square root property, move the 16 and take the square root of both sides, or you can factor difference of squares, x minus 4, x plus 4. So this is difference of squares, difference of squares. You set each individual again. X minus 4 is equal to 0, x plus 4 is equal to 0. And you solve simultaneously. X will give me 4 in this area, and then I will have an x equal negative 4. And I find exactly all of my 3 zeros. So one of the zeros will be 4 comma 0, negative comma 0, 4, negative 4 comma 0, and 5 comma 0. So these are my 3. That is 3 solutions, 3 zeros from this cubic function. Okay, so you have to factor, you have to set it equal to 0. Now, number 4, what happens once you factor? We have to look at the multiplicities. And what does that mean? That means how many potential zeros we can have, the multiplicity k. So we always have to have in this factored form x minus c, where c can be any value, even 0. So we want to first determine the zeros. So that means we're going to set f of x equal to 0. And then we are going to look at each individual multiplicity. So I'm going to pause the recording here to start this problem. Alrighty, so we left off talking about determining zeros and their multiplicities for this particular function, 8x parentheses x minus 1 squared, x plus 3 to the cubed. Now, what did we see on the last example? That if we have a factor of the form x minus c, which we have it in this form and this form, and it shows exactly k times. So k is the multiplicity. In this case, the multiplicity will be the exponent multiplicity of the zero. Let's write that down. So the first thing is to define the zeros of each. So f of x set it equal to 0. That means 8 of x parentheses x minus 1 squared x plus 3 cubed. So we have 8x is equal to 0. X has a multiplicity 1. X minus 1 quantity squared has set that equal to 0. And then we have x plus 3 cubed. Set that equal to 0. That means that this individual factor, x minus 1 set it equal to 0, I get x equal 1. So 1 will have multiplicity of 3. Multiplicity of 2. Why multiplicity of 2? Well, because the power of x minus 1 was 2. Now, if we have x plus 3, we have to first find the 0 of x plus 3. So we have x plus 3, set that equal to 0. That gives me x equal negative 3. So x equal negative 3, that's the 0. And the multiplicity is going to be 3. Why is the multiplicity 3? The multiplicity will be 3 because the exponent is 3. So if I do an extra step, an extra example, if I have f of x to be x cubed and then x minus 7 to the fourth, I have x equals 0 to be the 0 with multiplicity of 3, and x is equal to 7 with multiplicity of 4. How? Well, again, we first define the 0. X is equal to 0. That's one of the zeros. Would have multiplicity of 3 because the exponent of that 0 is 3. And then we have x minus 7, set that equal to 0. We get x equals 7, and that will have multiplicity of 4 because I have an exponent of 4. So then what does that tell us about the multiplicities and the zeros? How does that have, what effect does it have on the graphs? So notice that here, if we first find the zeros, so first we are interested in finding zeros. Find the zeros first. So we have x parentheses x minus 1, and then x plus 3 is equal to 0. They all have a multiplicity of 1. Look at the exponent. They don't have 1, so then the multiplicity will be 1. So x will be 0. X minus 1 equals 0. I get x equal 1. That's my other 0. And then I have x plus 3 equals 0. That's x equal negative 3. So there's negative 3. There's my 0. There is 0, another 0. And then I have positive 1. So notice that if it has an odd multiplicity, it's going to cross the x-axis. So if I have an odd multiplicity, it will cross the x-axis. So notice here that it crossed the x-axis, and then I have another 0 where it crossed the orientation from plus and minus, and then from negative to plus. So if we have an odd multiplicity, we will cross the x-axis. Now, what does that change on the next example? Here I have, again, finding the zeros. I have x is equal to 0 here with multiplicity of 1. Then I have x minus 1, set that equal to 0. I get x equal 1. That has multiplicity of 2. And then again, x plus 3, set that equal to 0. I get x equal negative 3. That's multiplicity of 1. If it has multiplicity of 1, that means it has odd multiplicity. So what do we know about odd multiplicity? So here we have negative 3. So because it's an odd multiplicity, it's going to cross the x-axis. See how it crossed? Now at 0, it also has an odd multiplicity because it has a multiplicity of 1. So it's also going to cross. But now at x equal 1, what happens at 1? Does it cross at 1? Here, I'm going to put it in blue. Does it cross? No. So if the 0 has an even multiplicity, it will touch the x-axis. So it will only touch it. You don't have to cross it. It will not cross the x-axis. It will only touch the x-axis. So that's the effect that we are going to see with zeros and their corresponding multiplicities. Let's go ahead and talk about that last polynomial. Again, first step is finding the 0 and their multiplicity. And the multiplicity. Let's go ahead and do that. So the first thing is I'm going to set k of x equal to 0. And then I said each particular term because it's in factored form. The nice part of this example is that they already in factored form. It says it's in format x minus c. So it's easy for you to find the factor. The first is my first 0 is x equals 0. It has multiplicity of 1, which is odd. So this one has odd multiplicity. X minus 1, set that equal to 0, I get x equal 1, which also has multiplicity 1. And then I have x plus 3, set that equal to 0, I get x equal negative 3. But negative 3 will have a multiplicity of 2. So if I have a multiplicity of 2, that means I have an even multiplicity. So at negative 3, I'm only going to touch at the point 0. I'm going to cross because, again, I'm crossing because I have an odd multiplicity. And last but not least, at positive 1, again, I'm going to cross because of the odd multiplicity. So please make sure that you are writing this down as we are going over this questions. And then note how the leading term changes the behavior. Now, our leading term would be x squared. So it's x times x times x squared. That's an x to the fourth. So it will behave as an x to the fourth. So the end behavior, if we remember, the end behavior of a positive x to the fourth would be as x approaches infinity, my function will also go to infinity. That's this endpoint right here. That's this side. And then as x approaches negative infinity, my function will also go to positive infinity. So I'm looking at this endpoint, this end behavior. I'm looking at this end behavior as I'm going to negative infinity. Now on this one, if I look at the end behavior of the previous, it's going to behave in x squared, and then another x. So x times x squared times x. This is an x to the fourth. So same thing, looking at the end behavior. And last but not least, this behaves as an x to the third. An x to the third, meaning that it's going to behave this way. So as x approaches infinity, my function will go to infinity. So I'm looking at this portion. If I'm coming from x going to the negative direction, then my function will also go to negative infinity, which I'm looking at this direction. So that would be my endpoint. So in this particular example, I looked for multiplicities, zeros, the effects, and I also talked about the types of end behavior, which we saw on that first portion. Now, what did we conclude? If a 0 has an odd multiplicity, it will cross the x-axis. If I have an even multiplicity, it will only touch the x-axis at that point C, at that 0. So question 5, I'm going to give you a few seconds to kind of work on it on your own, and then I will go ahead and review that. Alrighty, so hopefully you guys are working on this question. If you didn't have time to finish, that's okay. We're going to go ahead and go over it. So the first thing is to identify the zeros. So that means set f of x equal to 0. 0 will equal negative 3x squared parentheses x plus 4, x minus 7 to the cube. Now we wish to identify each of the zeros and their multiplicities. So step 2 is identify the multiplicity. So then what do we have to do now? So then we have negative 3x squared is equal to 0. That means that x is equal to 0. And we'll have a multiplicity of 2. Again, that means that we have an even multiplicity right there. Then we have x plus 4, that's raised to the first power, is equal to 0. So we have x equal negative 4. that will have the multiplicity of 1, which that's an odd multiplicity. And then last one is x minus 7, set that equal to 0, and I get x is equal to positive 7 with multiplicity of what? Of 3, right? Because it's odd, and k is to the third power. Now, determine whether it will cross it or it will touch. Well, that depends on if we have an even. So if we have an even, is it going to cross or touch at 0? So it's going to touch at the point x equals 0 because of the even multiplicity. It's going to cross at the point x equal negative 4 because it has an odd multiplicity. And at x equals 7, you will also cross because of odd multiplicity. Okay, so at 0, it's going to touch. At negative 4, it's going to cross. And at x equals 7, it's also going to cross. Okay. Now, the turning points of a polynomial functions are the points where the function changes from increasing to decreasing or vice versa. The turning points corresponds to the points where the function has a relative maximum and relative minimum. So that is the definition of what a turning point. The graph of a polynomial of degree, this is how you calculate or find the number of turning points. So you look at the degree of the polynomial and it will have at most n minus 1 turning points. So if we look at this question, give the maximum number of turning points for this function. So we notice that the degree of this polynomial is of f of x, leading term is x cubed, so n is 3. So the formula to find the maximum number of turning points, it's n minus 1. So it's going to be 3 minus 1. That's going to be 2 turning points. So notice that you have something that's increasing, then it's decreasing, and then increasing again. So increase, increase. I have a point right there, and then it starts to decrease, decrease, decrease. I have another point right there, and then increase, increase, increase. So changing orientation. So plus, minus, and then plus again. So that means that I will have 2 turning points, up, down, down, up. So I have a relative maximum and a relative minimum. So there's my relative maximum and relative minimum. That reflects those 2 at most n minus 1 turning points. Okay. Now, our goal is to be able to sketch a polynomial given these conditions. So in order for us to graph a polynomial function defined by y equal f of x, we need to first use the leading term to determine the end behavior, determine the y-intercepts, the real zeros or multiplicities, plot the x and y-intercepts to sketch the end behavior, start from the left end behavior, and then connect the x and y-intercepts. And then we also wish to test for symmetry, test whether f is an even function. So we are going to be using this formula to determine whether the function is symmetric towards the y, or if n is an odd function, it's going to be symmetric towards the origin. To finish off is to plot more points if greater levels of accuracy is desired. So right now we are going to be able to kind of sketch a polynomial function and locate turning points to kind of be able to see the figure of the graph of that polynomial function. Okay. So we are going to be using this 7 guidelines. So we're going to use this guidelines to be able to sketch a polynomial. So we are going to be looking at question 7, and we are going to sketch it completely. We are going to first talk about what's the general shape and who's going to give us the general shape. The general shape will be the leading term. So what is the leading term here? I have an x squared, an x, and an x. So x squared times x, that will be an x to the fourth. It's going to behave as an x to the fourth, meaning that it will have this type of shape, where I know that my end behavior is that as x approaches infinity, f of x will also go to infinity. As x goes to negative infinity, my function will also be positive infinity. Now, how many turning points? So it's going to be at most n minus 1 turning points, which is 4 minus 1, which is at most 3 turning points. Now we are interested in finding the intercepts. So we are going to find the x-intercepts by letting f of x equal to 0. Alrighty, so right now what we are doing is we are finding the x-intercept. So we are going to let f of x be equal to 0. So we have 0 is equal to x minus 1 quantity squared, x plus 3 times x minus 4. Now, using the zero product property, 0 is equal to x minus 1. We get x is equal to 1 with multiplicity of, and we already went over that. The multiplicity is 2, which is an even multiplicity. That means we are going to cross at that point. Excuse me, we are going to, because it's an even multiplicity, it will touch the x-axis. Now at x plus 3, set that equal to 0. There's my other 0. It's x equal negative 3. That has multiplicity of 1, which is an odd multiplicity. That means it will cross at the point negative 3. And then lastly, x minus 4, set that equal to 0, and I get x equal positive 4. So it also has a multiplicity of 1, which is an odd multiplicity. So it will cross the x-axis at that point. Now, if I want to find the y-intercept, you let x equal to 0. So f of 0 is equal to 0 minus 1 quantity squared times 0 plus 3 times 0 minus 4. That's going to give us negative 1 squared times 3 times negative 4. And that gives us a value of negative 12. So the point is 0, negative 12. So which points do we have? What type of points do we have? So we are going to have the point 1 comma 0, negative 3 comma 0, and 4 comma 0. So let's go ahead and plot that. So 1 comma 0, we have negative 3 comma 0, we have 4 comma 0, which are my x-intercepts. Now my y-intercept is negative 12, but be careful. This is 10, negative 10, negative 20, negative 30, negative. These tallies are worth 10 points. So negative 10, negative 12 will be somewhere here. Now then, we're looking at the end behavior. So what do we know about the end behavior as x approaches negative infinity? So if it's coming from this side, my function f of x is also positive. Now we wish to find a value between a turning point. We want to find the value. We know that at this point, at x equal negative 3, it will cross because it has odd multiplicity. So we know it's crossing it. So we are going to substitute a value right in between -3, and 0. So let's go ahead and substitute -2. -1, -2. So what happens at -2? So we want to test. So at -2, I have -2 minus 1 squared times -2 plus 3 times -2 minus 4. I have -3 squared times a +1 times a -6. So I have 9 times 1 times -6, which is -54. But remember, this is -10, -20, -30, -40, -50, -54. So around down here. So if we graph, let me remove this part. So if we wish to graph at -2 down 54, it's coming from here. We'll have a turning point. We are going to cross here, so we're going to have this beautiful shape. And then what else would it happen? Well, then at what happens at this point? What happened at x equal 1? Will it cross or will it touch? Well, let's go back. At 1, it will only touch. So you're just going to touch it. And then what happens? Well, what want to know what other point between x equal 1 and x equal 4? Let's plug in x equal 3. So now we have f of 3. We want to test. So these are testing points. F of 3 would be 3 minus 1 squared, parentheses, 3 plus 3 times 3 minus 4. That's going to give us 2 squared times times 6 times a -1. So then that's -24. So down here, remember, at now 3, 1, 2, 3, 24, negative. So it's going to be somewhere here, down 24. So it's going to touch and then it's going to go down and then up again. Because how do I know it's going to go up again? Because of my end behavior. So my end behavior tells me that this is going to keep increasing because as x goes to positive infinity, my function will also go to positive infinity. What else do we know? We know we will have 3 turning points. My first turning point is the minimum, max, and then another minimum. So I have 1 turning point, 2 turning points, 3 turning points. So turning point 1, turning point 2, turning point 3. So we had to find a number between, we had to test a number in between -3 and 0. And then again, we had to test a number between, in this case, it was 1 and 4. Test a number between 1 and 4. And we chose 3. You could have chosen 2. That could also work. But in this case, we chose f of -2. So when we substituted f of -2, we had -2 minus 1, that's 3 squared, -2 plus 3, that's a +1. And then we had -2 minus 4, which was a -6. So we had a -54. Okay. So then when we are sketching, we still are going to have to use some test points. Alrighty, let's look at number 8. We are going to do the same thing. We're going to say, okay, well, what's the general shape? We'll start with what's the general shape? Well, what the general shape is, I have a negative value, negative first power, negative x times a x squared. That's going to be a negative x to the cube. So if we have a negative x to the cube, alrighty, so finishing example number 8, we have a leading coefficient that is negative, and we have an odd polynomial. So if we're looking at the end behavior first, the end behavior of an odd polynomial with a negative leading coefficient is as x approaches infinity, my function will go to negative infinity. As x goes to negative infinity, my function actually will go to positive infinity. So it's going to look like if it's coming from negative infinity, my function will actually come from above and then have this behavior. So as x goes to infinity, the function will go to negative infinity. As x approaches negative infinity, my function actually will be positive. So we will have a behavior that looks like this. So what we want to do next, right, is find how many turning points. So if we're looking for turning points, is n minus 1 at most turning points. So n is the degree of the polynomial. So the degree of the leading term. So we have the degree of that polynomial. So the degree, so we have 3 minus 1. That's going to be at two turning points. So if we're looking at 2 turning points, we know that the behavior is going to have a maximum and a minimum. So then the next step is to find the x-intercepts and the y-intercepts and determine the multiplicities of those x-intercepts. So if we rewrite the function, we have 0 is equal to negative x, negative x plus 1, parentheses x minus 3 squared. So we have x plus 1, set that equal to 0. I get x equals negative 1 with a multiplicity of 1. That means we have an odd multiplicity. That means it's going to cross the x-axis. And x minus 3, set that equal to 0. I get x equal 3. That will be my 0. But this time it will have a multiplicity of 2. If it has a multiplicity of 2, that means I have an even multiplicity. If I have an even multiplicity, that means it will only touch at that point. So then what do I have to do first? Well, I know that I'm going to have to find the now y-intercept. So to find the y-intercept, you let x equal 0. So f of 0 is equal to negative 0 plus 1, 0 minus 3 squared. So it's negative 1, and then negative 3 squared, that's a positive 9, that's negative 9. So negative 9 would be the y-intercept. So 0, negative 9, that's my y-intercept. My x-intercepts are negative 1 comma 0 and 3 comma 0. So let's go ahead by start sketching these. So I'm going to highlight my y-intercept and my x-intercepts. So negative 1, 0, there it is, negative 1, 0. Negative 1, 0, and then 1, 2, 3. Now at negative 1, we know it's going to cross. So I want to know the end behavior as well. The end behavior, we know it's going to come from above. Now I want a value right in between. I want to test a value between negative 1 and positive 3. So if we choose a testing point, again, I wish to test a point at 0. So if I test it at 0, what is f of 0? No, f of 0 we already know. F of 0 was my -9, my y-intercept, so we can't test that one. So this is -5, -10, -15. This is by 5s. So down here, it's going to go this way. Now, what's a number between 0 and 3? So I'm going to test 2. So find f of 2. That's going to be my testing point. So what happens at f is equal to 2? So it's going to be a -2 plus 1, close it, and then 2 minus 3, quantity squared. So this is -3 times -1 squared. That's going to be -3. So it's going to be at 2, it's going to be -3. So I know here I'm going to go up, passing that. And now what's going to happen at 3? At x equal 3, I'm only going to be touching it. So if I'm touching it, I know my end behavior says that as x approaches -infinity, as x goes to positive infinity, that's as x approaches positive infinity, my function f of x will decrease. So then right after it touches, so it touches here, but it will cross here. And I have 2 turning points. So there's my 2 turning points. Down, up, down. I have a turning point here and a turning point here. And that's n minus 1 turning points, which corresponds exactly to what I want. So what we actually had to do was actually test a point right in the middle between 0 and 3, and we tested 2. And with that, we are able to sketch. Now the next thing, the last part of this section is to look at the intermediate value theorem. And what does this intermediate value theorem say? Let f be a polynomial function for a being less than b. So we have an interval where a is -1 and b is 0. So we are going to have to test f of a and f of b. They must have opposite signs. Then f has at least 1 0 in the interval. So once we find f of a and f of b and they have opposite signs, then we know for a fact that this function, this polynomial function, will have at least 1 0 on the interval. So what we are going to do is we are going to be applying the intermediate value theorem. We are going to see whether it's true or not. So we must have an interval where a is less than b. So here we have -1, 0, where a was -1 and b is 0. So a is less than b. That's true because -1 is less than 0. Now we have to find f of a. That would mean f of -1. So let's plug in f of -1 into the polynomial. -1 cubed minus 13 times -1 squared plus 33 times -1 plus 35. And let's find that value. So here we have a -1 minus 13 times 1 minus 33 plus 35. So let's go ahead and pull out our calculator. What do we get? When I substitute and find the value, we get -12, which is a negative number. Next, we apply f of b, which is f of 0. So what's f of 0? F of 0 is 0 cubed minus 13 times 0 squared plus 33 times 0 plus 35. Now these will all drop, and I'm only going to be left with 35. So f of 0 will be 35. And then what did we say about the comparison? F of A was equal to -12 versus f of B was 35. Are they different in signs? So signs are opposite. What does that mean? since the signs are opposite, then the intermediate theorem, IVT, the intermediate value theorem applies. That means we are guaranteed to have a zero right in between -1 and 0. And then how can we test it? We can actually test it by actually graphing and determining that we will indeed have a 0 in the graph. So let's go ahead and open up my window, my calculator window. So I will open Calculate 84. And I have it right here. So I have y equals, I'm going to remove everything that I have on the screen. And I will have x, erase that to the third power, minus 13x squared plus 33x plus 35. And then I'm going to select graph and see how if I zoom in, I actually will have 3 zeros. But it's saying I have to look at a specific interval between -1 and 0. So between -1 and 0, I know that there is going to be an x-intercept. So if we plug in, let x be 0. So I'll trace, let me go zoom, trace value. I'm going to put x equals 0. So if x is equal 0, y equal 35. But now if x is 0, so there is an interval here, but between -1, if I zoom in, I'm only looking between -1 and 0. Notice that there is a x-intercept right there. That tells you that the intermediate value theorem does apply. And with that, we finish section 2.2. Thank you, and I'll see you guys next time. Bye-bye.